So here we are on the home stretch with power series. Today we're going to look at Taylor series and some approximation stuff, and also some kind of cool examples right there at the end, bonus stuff, as we bring this home, wrapping up this crazy little series on I guess, on the Swiss Army knife, the duct tape of mathematics, the power series. Power series, so Taylor series and approximations. So we've learned about power series, and we've done this in two steps. We learned to find the power series. We did this mostly using geometric series or Maclaurin series, and then whatever algebraic manipulations we could do to those. And then we found where those series were convergent. The second point, and the interval of convergence, provides us a clue toward our next step. Example 1. Review two power series for 5 over 4 plus x. You may recall that 5 over 4 plus x was one of the examples we looked at in a previous example. And we found earlier, or we at least claimed earlier, that this was equal to the sum from n equals 0 to infinity of 5 times negative 1 to the n times 3 plus x quantity to the n. Earlier, we found that the interval of convergence for this was negative 4 less than x less than negative 2. And you'll notice that halfway in between this negative 4 and negative 2, the exact midpoint, would be where x equals negative 3. And in particular, notice that if you take that negative 3 and you substituted it in to the power series, you get a 3 plus negative 3, and 3 plus negative 3 is 0. So it's kind of an indication of where the center of this first series is. We also have that same series, 5 over 4 plus x, could be written as using another version of the geometric series as the sum from n equals 0 to infinity of 5 over 4 times the quantity negative x over 4 raised to the nth power. We didn't go over this one earlier, but you should be able to see that you could factor a 4 out of the denominator. That gives you that 5 over 4. And then you could rewrite the plus x, which is now a plus x over 4, as a minus x over 4. And hence, that's where the negative x over 4 comes from. Here, we've done enough questions like this to notice that our interval of convergence will be from negative 4 to positive 4. And the center of that region between negative 4 and 4, the center of that would be at x equals 0. Notice again that if we took that x equals 0, and we substituted it into the power series that we found, it will give us a 0 over 4, or like a 0 to the nth power. It's kind of the same type of thing. So before we move along, notice that this means that there are multiple power series. Each power series comes with its own interval of convergence. Generally speaking, a bigger interval is better. And each interval has its own center. Okay. So the power series representation for a function is not necessarily unique. Notice that one function may have more than one power series representation. These series have different intervals of convergence. And of particular note, the center of the intervals of convergence is different, right? Both at 0 and negative 3. And so this is our first hint of this idea of a center of an interval of convergence, which is going to be a big thing in our next topic, the Taylor series. Historical note. One of the most innovative aspects of Cauchy's limit-focused program of rigor was his rejection of divergent series. These had been widely used in the 18th century before Cauchy declared that they were unacceptably ill-defined and produced ambiguous or even erroneous results. Picking up on these points, on this point in several papers of the early 1830s, Poisson tried to come to a clear understanding of these series and the boundaries of their legitimacy. In his 1844 paper on divergent series and various points of analysis connecting with them, De Morgan blasted not only Poisson's ideas and Cauchy's definition of the integral on which they were based, but the whole preoccupation with certainty which valorized the search for a rigor. Divergent series, at the time Poisson wrote, had been nearly universally adopted for more than a century, and it was only here and there that a difficulty occurred in using them, De Morgan fumed. The knowledgeable mathematician De Morgan pointed out, could easily detect and correct such problems when they arose. To artificially control their use just in order to guarantee rigorous exactitude was at best unnecessary and ridiculous. At worst, it could stand in the way of deeper understanding of the truth embodied in these theories, which was as yet still poorly comprehended. As De Morgan wrote, we must admit that many series are such as we cannot at present safely use except as means of discovery, the results of which are to be subsequently verified. But to say that what we cannot use, no others ever can, to refuse that faith in the future prospects of algebra, which has already realized so brilliant a harvest, seems to me a departure from all rules of prudence. For De Morgan, to draw back from poorly defined or understood mathematical conclusions was a grievous error. It's this long quote, so let me see if I can summarize. Calculus is invented or discovered first by Isaac Newton in the 1660s. And it starts in the 1660s, and there's lots and lots of use of power series for the next 150 years. And while they're doing this, they don't really worry about where the series converge or where they diverge. They just kind of use them, and their intuition is good enough that they mostly don't fall into any traps. But in the early 1800s, Cauchy comes along and wants to have a more rigorous foundation for math. And so he starts to build everything upon the limits, and he makes a big deal of the idea of a convergent versus a divergent series. And he says we shouldn't be doing anything with divergent series. But what this long excerpt from the article makes clear is that even in the 1830s, 40s time, you have De Morgan, a big mathematician in England, who still thinks that it's okay to use divergent series. So 150 years, or more than 150 years after calculus was invented / discovered, you still have mathematicians that are kind of being sloppy and using these divergent series willy-nilly. Today, that would not be acceptable. Today, it's kind of hard to believe that any self-respecting mathematician would want to do stuff with divergent series. But that's the way the history is. The history says, first they found the power series, and then it was only later that they came back and decided to be really careful about determining where the series converge or diverge. Back to power series and the center of the power series. So this idea of the center of a series is not new to us. This isn't the first time we've generated a power series with a known center point. In particular, the Maclaurin series formula, f of x equals to the sum from n equals 0 to infinity of the nth derivative of f evaluated 0 times n factorial, or over n factorial, times x to the n, generates a series centered at x equals 0. To see this, notice here's the x equals 0, there's the 0, and also note that if we were to take this x equals 0 and substitute it into the power series, each of the terms would include a 0 to the nth power. This formula and the accompanying derivation that we already went through can be modified to generate series centered at x equals a, so a shifted series. So definition, if f has a power series representation or power series expansion at x equals a, that is, if f of x equals the sum from n equals 0 to infinity of Cn times x minus a quantity to the nth power, when the absolute value of a minus x minus a is less than r, then its coefficients are given by the formula Cn equals the nth derivative evaluated at a divided by n factorial. We call the series above a Taylor series. So that definition is a little bit wordy. It's a little hard to see what's going on. But what I'd like to do is point out the difference between the Maclaurin series, where we're evaluating the function at 0, and the Taylor series, where we're evaluating the derivatives at a, as well as the Maclaurin series, where we have an x. Notice x to the n is the same as 0 to the n when x equals 0, centered at 0, versus the Taylor series, which has an x minus a to the n. Notice when x equals a, center of that series, this would evaluate to 0. So it'd be a minus a raised to the n, or 0 to the n. So in truth, this Maclaurin series is actually a special case. Special case of the Maclaurin series, or of the Taylor series. When a equals 0. Example 2. Find the Taylor series for f of x equal to 1 over the square root of x, centered at a equals 16. So this is going to begin very similar to our derivation of the Maclaurin series. So we have f of x, which is equal to 1 over the square root of x, or maybe x to the negative 1/2 power. So we got to find some derivatives. So f prime of x will equal negative 1/2 x to the negative 3/2. F double prime will equal, looks like 3 over 2 squared x to the negative 5/2. F triple prime will equal negative 3 times 5 over 2 to the 3rd power, x to the negative 7/2. That was the triple prime. The 4th derivative will be positive 3 times 5 times 7 over 2 to the 4th power, x to the negative 9/2. Okay, so we've got our functions. Notice our pattern. You've got a 3 times 5 times 7, 3 times 5, 3. We could actually recognize that we could add in a 1 here. So it's 1 times, 1 times, 1 times, 1. And so you could see that it's kind of like a factorial, but instead of it being a factorial of every integer, it's just a factorial of the odd integers. In this case, starting at 7, then 5, then 3, then 2. Kind of a weird thing. So we have our derivatives, and now we need to evaluate those derivatives at a. So here we're going to go at a equals 16. So 16 to the negative 1/2, this would be like 1 over the square root of 16. 1 over the square root of 16 would be 1 over 4. And then we have minus 1/2 times 1 over, I want 16, I've got 16 times 4. Maybe I'll write that as 4 cubed. That might be a little easier. So if I have 4 cubed, and then 1 positive 1 times 3 over 2 squared times 1 over 4 to the 5th power, and then 1 times 3 times 5, but negative, over 2 cubed. times 1 over 4 to the 7th power, and 1 times 3 times 5 times 7 over 2 to the 4th power times 1 over 4 to the 9th power. Whew. Okay. So if we want to find our Taylor series using all this, remember these values here will give us our coefficients. These are coefficients. Maybe we'll color code them individually. So let's see if we can put all this stuff together. What we're saying is that 1 over the square root of x is equal to 1 over 4 minus, so here's the 1 over 4, and then minus, and then we have a half times 1 over 4 cubed times x minus 16 all over 1 factorial. And so that's this bit right here, showing up right here. And then we can add in 1 times 3 over 2 squared times 1 over 4 to the 5th. So that's our third function. But then we're going to divide that by 2 factorial and multiply it by x minus 16 squared. Okay, we're on a roll. So then we would subtract. I'm going to just go to a new line. Subtract 1 times 3 times 5 over 2 cubed times 1 over 4 to the 7th all over 2 cubed. So that's this thing right here. Okay. We divide the whole thing. Oops. Sorry. Not 2 cubed in the denominator. 3 factorial. And I multiply the whole bit by x minus 16 cubed. And then we could add 1 times 3 times 5 times 7 over 2 to the 4th power times 1 over 4 to the 9th power all over 4 factorial times x minus 16 to the 4th, etc., etc., etc. Here that quantity, I guess that's the blue quantity. So you'll notice that the denominators, the 1 factorial, 2 factorial, 3 factorial, 4 factorial, etc., those are coming from the formula, and similarly, the x minus 16 to the 0th power, x minus 16 to the squared, x minus 16 cubed, etc., etc., etc. Those are coming from our formula. If we back up, you can see that we have a power series representation for 1 over the square root of x. And it's centered, it would be all of those terms are going to be 0 when x is equal to 16. Notice that at 16, the two match. So at 16, you'd have 1 over square root of 16, or 1 over 4 equals 1 over 4 plus a whole bunch of zeros. Example 3. Find the Taylor series for g of x equal to x minus x cubed, centered at a equals 2. So this question is going to begin like the last one. So we have g of x equals x minus x cubed. G prime of x will equal 1 minus 3x squared. G double prime will equal negative 6x. The third derivative will equal negative 6. And the fourth derivative will equal 0, as will all the ones after it. Okay? We can evaluate these, when are at a equals 2. So a equals 2. So g of 2 would be 2 minus 8, negative 6. G prime would be 1 minus 12, minus 11. G double prime, negative 6 times 2, negative 12. G triple prime, negative 6, and then 0 from that point forward. So if we put all this stuff together into a Taylor series, what we're saying is that g of x, which is x minus x cubed, is also equal to negative 6 plus minus 11 times x minus 2 all over 1 factorial minus 12 times x minus 2 squared over 2 factorial minus 6 over 3 factorial times x minus 2 cubed plus 0. All the other coefficients will be 0. So here we have a second representation, a second Taylor series for g of x. Notice again that your denominators are going to be divided by 0 factorial, 1 factorial, 2 factorial, 3 factorial, and you have those, the x minus 2's from the formula that are sitting in with each of the terms. X minus 2 to the 0, x minus 2 to the 1, x minus 2 to the 2, x minus 2 to the 3, plus 0, 0, 0, etc., etc., etc. So there we found a Taylor series for g of x equal to x minus x cubed, but this time centered at x equals 2 instead of centered at 0, like the original function that we're given. Now, the next question asks us to answer the following for f of x equals 1 over square root of x. When we're looking at the Taylor series centered at x equals 16. And this is the same question we looked at earlier. So before we go back, before we go on, I want to go back and simplify it briefly. So let's scroll back and notice that we had all of these ugly coefficients, which could be simplified. And if you know if you've been around computers a little bit, you might recognize that these are all powers of 2. So this is like 1 over 2 squared, negative 1 over 2 to the 7th power, 1 times 3 over 2 to the 12th power. We're going up by 5 each time here. Minus 1 times 3 times 5 over 2 to the 12 plus 5 would be 17th power. 1 times 3 times 5 times 7 over 2. 17 plus 5 is the 22nd power. So those are our coefficients. I've just cleaned them up a little bit because they will help us in our next example. So here we are in this next example. We want to find the Taylor polynomials T0, T1, T2, T3 centered at x equals 16. So this looks a little scary. It might even look like a bunch of Terminator movies to some of you, but this is actually pretty straightforward. So we look at T0. T0 is simply the Taylor polynomial that just includes the very first term. So in this case, T0 will be 1 over 2 squared. So again, T0 is just the very first or the 0th term in the Taylor series. So there's your T0. So then if we look at T1, T1 will equal the first term, 1 over 2 squared. And then we have minus 1 over 2 to the 7th power divided by 1 factorial times x minus 16. And so this would be your T1 term. And notice it's T0 plus something else. Here's the 1 factorial that's built into the formula, and you have the x minus 16 that's again built into the formula. Now we can look at T2. So T2 is going to be T1, which is 1 over 2 squared minus 1 over 2 to the 7th over 1 factorial times x minus 16. And then we're going to go plus 1 over 2 to the 7th to the 12th power over 2 factorial times x minus 16 squared. Let's clean up that squared. And so you can see that T2 would be the 2nd degree Taylor polynomial. It's not the full series, it's just the first, it's just the quadratic version of what's going on. In T3, same thing is going to happen. So we'll have T3 equals 1 over 2 squared. Maybe we could clean this up a little bit. So it'd be 1 over 2 to the 7th times 1 factorial, x minus 16, plus 1 over 2 to the 12th times 2 factorial, x minus 16 squared, plus minus 1 over 2 to the 17th times 3 factorial, x minus 16 cubed. So I think you should get the pattern here that T sub n, I forgot something. I got to come back and fix something. T sub n is the nth degree polynomial. If you've been tracking right, you realized I forgot something in my coefficients. It should be my coefficients, the numerator should be 1, and then 1, and then 1 times 3. 1 times 3, and then, strut. Sorry, I gotta get them in the right spot. Sorry, it should be, so it's 1 for the first one, 1 for the second one, the third one is 1 times 3. The fourth one is 1 times 3 times 5. Sorry about that. I forgot these parts of the coefficients just in the copy from one part of the notes to the other. So again, Tn would be an nth degree Taylor polynomial. It's not the whole Taylor series, it's just the first few terms up to power n. So an interesting mathematical side note on how to write the product of evens or odds. You might say, why are we doing this? It's because we had that numerator. In our numerator, we were ending up with 1 times 3 times 5 times 7 times 9 times, et cetera, et cetera. So you might be like, how do I write that? It's sort of like a factorial, but it's only the odd terms. So here's a couple of little examples. Notice if we have a whole bunch of evens here, 12 times 10 times 8 times 6 times 4 times 2, each of those terms has a power or a factor of 2 in it. So this is like 12 is 2 times 6, 10 is 2 times 5, 8 is 2 times 4, 6 is 2 times 3, 4 is 2 times 2, 2 is 2 times 1. And so if you add these up, this would be 1, 2, 3, 4, 5, 6 powers of 2, or 2 to the 6th. And 6 times 5 times 4 times 3 times 2 times 1, or 6 factorial. So that's how you could write kind of an even double factorial out. If you wanted to do the same thing with the odds, we got to play a little game. So we can take the odds, the 9, 7, 5, 3, and 1, and we recognize that that's sort of like 9 factorial, but there's a whole bunch of extra terms. So it's math. If you want something, you can have it. So we insert all the missing terms, but in order to insert them, we have to also divide by 8 times 6 times 4 times 2. So the numerator up top is now conveniently just 9 factorial. And we earlier showed how to write out kind of this double factorial with all even numbers. So that would be 2 to the 4th times the 4 factorial after you factor out the 2 out of each of the numbers. So that's kind of a quick way of writing things succinctly. Quick being in quotes. Part B. Use T0, T1, T2, T3 to approximate 1 over the square root of 16.8 and 1 over the square root of 22. Then compare these approximations to the calculator value and list the errors. Note that the absolute error is the difference between function value and the value the Taylor polynomial provides us. So I took the liberty of typing these functions into the calculator kind of on my own time. So let me share those with you. So here is our T0. Here's T1, and you'll notice that what T1 is it's Y1. So this would be like T0 minus, and then I took the liberty of writing things a little bit more simply just for the sake of clarity. And then here's T2 in Y3, and notice it references T1 and then just adds on another term. And T3 references T2 and then just subtracts another term. So I have found my, I've entered my T's into the calculator, and then I can go over to my table. And I've let my X be 16.8 and 22. Those are the two values I care about. And this tells me here's the T0 approximations for both. Here's T0. Here's T1. Here's T2. And here's T3. And just by way of reference, we're trying to compare. Notice that 1 divided by the square root of 16.8 is, this top one would be like 0.24398. 24398. 8, etc., etc. And the second one to 5 places would be 0. So this is 1 over the square root of 16.8. And let me switch colors. And then here, 1 over square root of 22 will be 0.2132. 2132, and it's actually 2320. And you'll notice if you look at the approximations that the top ones look pretty good, pretty fast. The bottom ones don't look, they still look pretty good, but they're not quite as good as before. So let's go back to the notes and see if we can fill all this stuff in like we were asked to. All right, so we want to look at T naught, T1, T2, and T3. And we want to ask, we want to ask what happens when we look at 1 over the square root of 16.8. Okay. And so that would give me 0.25 even. And then the next one over to 4 decimal places would be 0.2437 or 38. And the next one over would be, next one over would be 0.2440. And the next one over would be also 0.2440, just rounding to 4 decimal places. And by way of reference, we have that to 4 decimal places, this is equal to 0.2440 using the calculator. So notice we matched our calculator value with our T2 approximation, which is pretty cool. A quadratic was good enough to give us a pretty good approximation of square root of 16.8. How about if we looked at 1 over the square root of 22, which is 0. To 4 decimal places, 0.2132. So T naught in this case is going to again be 0.25, because remember, it's just a quarter, it's a constant function. And then T1 would be 0.2031. And then T2 would be 0.2163. And T3 be 0.2122. So if you compare that to the actual value calculator gives to 4 decimal places, you can see that the cubic is close, but it's still not quite there. It looks like maybe one more term and we would have a pretty good approximation of 1 over the square root of 22. So let's think about the error. We look at the error. So the error is going to be the difference, and what we care about is the error in absolute value. So if we look at the 1 over square root 16.8 error, this is going to be, it'd be like, how do I want to say this? It'd be like 1 over the square root of 16.8 minus 0.25, but I want it in absolute value. So my error would be 0.006. And then if I did this at 0.2438, my error would be 0.000175, or I think I'll just go with 2. And then if I did this at 440, my error is going to be 0.00002. And I think the same thing's below. Actually, it would be less if we had more decimal places. But you can see that there's a pretty small error if we match the column of the approximate values. We ask, what is the difference between the actual and the initial? Maybe you're not seeing it. So error is equal to the absolute value of the actual minus the approximation. Because of the absolute value, it doesn't matter which one comes first. So now we could do the same thing, but with the 1 over square root of 22 error. So I have 1 over square root of 22, and if I subtract 0.25, I get that my initial error is 0.0368. Again, this is absolute value, so I'm not worried about the sign. 0.2031. Second one, I have error of 0.0101. Next one, 2163. 0.0031. So notice the error is getting smaller each time. 0.0010. So this is our error from the 1 over square root of 22. Okay, so we have found the calculator values. Just to be clear, we found our calculator values. That's in these first 2 columns. And then we found our errors, list our errors. That's in our second 2 columns. So it's our second 2 columns. And I simply want to point something out to try to make a connection between what we're doing here and what's happened elsewhere. What I want to point out is that there's bigger error. So this was a Taylor series. Taylor series or Taylor polynomials centered at x equals 16. So then we looked at 2 different specific x values. So we looked at 1 over the square root of 16.8. This would be like saying x equals 16.8. And we also looked at 1 over the square root of 22. This would be like saying x equals 22. And what I want to point out is that in the case of the red one, 16.8, we're very close to the center point of x equals 16. We're close, and we have pretty small error. But then when we looked at x equals 22, here we're far from 16. Now we're almost 6 units away. And so it shouldn't surprise us that we have a larger error when we are farther from the center point of our series. So all that to say, one of the advantages of having thinking about the center of a Taylor series is that your approximations, when you use just a Taylor polynomial, part of the Taylor series, your approximations will be better when you are close to that center point. Even if it converges absolutely, sometimes if you go, it'll take a lot of terms in order to converge or be close if you're far from that center point. There's a problem. Taylor polynomials and power series allow us to generate these approximate values like we just saw. However, these are estimates. How close are the approximate values to the actual values? Well, in order to find that error, we would need to know the exact value. We used our calculator. Actually, that doesn't give an exact value. That is giving an approximation. But anyway, we would need to know the exact value. But if we knew the exact value, we wouldn't need an estimate in the first place. So to figure out how good our approximation is, you need the actual value. Why are you looking for an estimate if you have the actual value? There's something really weird about this. We need a way to find the error that does not require that we know the exact value. Or to be more precise, we need a way to bound the error. So we need to find the error that does not require that we know the exact value. We need to bound the error and say the error is at most such and such. In engineering, I think sometimes this is called tolerance. Like we have a tolerance of up to this amount. This much leeway, if you will. In order to find this, we're going to need to build up a little bit more notation. So this next definition helps me understand what the remainder is in the context of a Taylor polynomial. So definition: the f have continuous derivatives up to the n+1th derivative on an open interval I containing a. For all x in I, f of x equals the nth Taylor polynomial of x plus the remainder evaluated x, where Tn is the nth degree Taylor polynomial for f centered at x equals a, and r of x is the remainder. So T is the Taylor polynomial, and r is the remainder. So to be clear, when we're doing this, we're saying that we have our f, which gives us the exact value. That's what we really want to find out. We're going to approximate it with some t, but we know that our approximation is off by some amount, is off by some error margin, which we call the remainder, or the error. So let's look back at our example 2 and try to understand this definition. So example 2 revisited. Find R3, the remainder, for the third degree Taylor polynomial of f of x equal to 1 over square root of x, centered at x equals 16. So let's start by writing out the Taylor series, maybe the Taylor polynomial. And I'm going to write it with some, I'm going to keep simplifying my notation to save ourselves a little bit of writing. So we're saying that 1 over the square root of x is equal to 1 over 2 squared minus 1 over 2 to the 7th times 1 factorial. 1 factorial. And then we also have a x minus 16 plus 1 times 3 over 2 to the 12th times 2 factorial times x minus 16 squared minus 1 times 3 times 5 over 2 to the 17th times 3 factorial x minus 16 raised to the third power. And this is our third degree polynomial, but we could keep going, right? We could say plus, the next one would be 1 times 3 times 5 times 7 over 2 to the 22nd times 4 factorial times x minus 16 to the fourth minus dot, 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 dot. So each time you can see those numerators are kind of that odd double factorial. You have a 2 to some power times a factorial, and then x minus whatever, x minus 16 raised to whatever power. Okay, so this part on the front end, there, that is our T3. And so the part on the back end goes forever, that must be our R3. So if we want to find R3, we can now see it. R3 of x will equal, the first term is going to be 1 times 3 times 5 times 7 over 2 to the 22nd power times 4 factorial times x minus 16 to the fourth power. And then we could just catch the pattern. So the next one part would be 1 times 3 times 5 times 7 times 9 over 2 to the 27th power times 5 factorial times x minus 16 to the fifth. And then it would go plus, you want one more term, it'd be like 1 times 3 times 5 times 7 times 9 times 11 all over 2 to the 32nd power times 6 factorial times x minus 16 to the sixth. And then it's going to keep going forever and ever. This one has a dot, dot, dot. So notice that the Taylor polynomial, here, T3, it ends, like it stops at the third degree thing. But the other term, I don't know what color it is, the R of 3, maybe it's blue, it's going to go on forever and ever, right? Here's your R of 3, and it's, notice there's this dot, 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 dot that just goes on forever and ever. It keeps going and going and going, like the Energizer Bunny. So the Taylor polynomial, that's just the chunk of the Taylor series, truncates, it ends. The remainder is everything else. So notice that finding R of 3, this is the remainder, or you might call it the error. So it requires knowing, like, to actually figure out a number for R of 3 requires either evaluating an infinite sum, that's one option, that's difficult, or it requires knowing an exact value, in this case an exact value of 1 over square root of x. And in this case, we can actually use our calculator to evaluate 1 over square root of x and get some sort of a value that at least is good to, 13 decimal places. But what if we didn't have the ability? What if we didn't know the exact value? How would we be able to say something about the remainder, about the error in that case? The remainder estimation theorem. Suppose there exists a number, big M, such that the absolute value of the n+1th derivative of f of x is less than or equal to big M for all x in the interval a minus c to a plus c. The remainder of the nth degree Taylor polynomial for f centered at a satisfies the absolute value of Rn of x is less than or equal to big M times the absolute value of x minus a, all raised to the n+1th, over n plus 1 factorial. Whew, that's a mouthful. Let me just make one note about this definition, actually maybe two notes before we continue on with it. So the first one has to do with this interval from a minus c to a plus c. So if you picture a number line here, the x, and here is an a, then you could go a plus c would be over here on the right, and a minus c would be there on the left. And so all we're saying is that we're on an interval of where kind of like the radius of, sort of like a radius of convergence, but not quite, but an interval where that's centered at A and goes C to the right and C to the left. The second thing is that this inequality up here, where you have the absolute value of the n plus 1th derivative of f of x, all less than or equal to m, gives you the m part of the formula below. So we're going to use the n plus 1th derivative to find the m. You're always going to have the second part of the formula, which is the absolute value of x minus a raised to the n plus 1 over n plus 1 factorial. Example 2 revisited again. So we want to bound the error in T3 on the interval 9 less than or equal to x less than or equal to 22. And we want to find the upper bound, that is the max error in our estimates for 1 over the square root of 16.8 and 1 over the square root of 22. So let's see what's going on here. So 9 to 22. This is x. So we're going from 9 to 22. I think this is the typo. This is supposed to be a 23. I'm sorry. 23. So halfway between 9 and 23 would be 16. So there's our series centered at 16. And so we went 16 plus 7 and 16 minus 7. So that's this region here. And we want to find the upper bound or the max error in our estimates. So we need to find our big M. And notice in this case, we were told that we're working with T3. So the first thing we were going to do is we're going to think about our interval. We already did that. The second thing we're going to do is we're going to find our big M. Okay, so we know that we know that our n plus 1th derivative, of f has to be less than or equal to big M on the given interval 9 to 23. Okay, and so this will help us find that big M. So how are we going to do that? Well, in our case, the n is going to be 3. So we need the 4th derivative of f, and we've already taken our 4th derivative. Our 4th derivative of f will be, oh my gosh, let's see. So this would be, I think I've got 1, pardon me, I'm losing it. I gotta think this week. It's my scratch work. So we had x to the minus 1/2. That was our original function. our first derivative was minus 1/2 x to the minus 3/2. That was our first derivative. Then we had our second derivative, x to the 5/2. So this is our original function, f prime, f double prime, f triple prime would be, looks like the 3 times 5 over 4 x to the minus 7/2, and the fourth derivative will be negative 3 times 5 times 7 over 8 x to the negative 9/2. Okay, so we know that the fourth derivative of x is going to be, what did we just say, negative 3 times 5 times 7 x to the negative 9/2 over 8. Okay, so what are we going to do with that? And we're looking at the absolute value of this thing. And let's see if we can rewrite this. So this thing will be less than or equal to m. So this would be like, the absolute value doesn't matter. So this would be 3 times 5 is 15, times 7 is 105. So I have like 105 divided by 8 x to the 9/2. All in absolute value is less than or equal to m. And we're on the interval 9 to 23. Okay, so notice that your x values are in the denominator. And so the bigger your x values are, the bigger that denominator is, and so the smaller the overall quantity is going to be. And so this is going to be greatest, in this case, because the function is decreasing, this is going to be greatest when x is smallest on the interval, that is when x equals 9. Okay, so we want to be the greatest because we want it to be the greatest because we're looking for big M, which is going to be bigger than everything else. So this tells us that our big M, we get to choose it. So we're going to say let big M be equal to 105 divided by 8 times 9 raised to the 9/2 power, which if we found a decimal, that would be about 105 divided by 8 times 9 to the 455, or it's a pretty small number. So I've got 0.000668682. So I'm saying my fourth derivative is always smaller than or equal to this thing on the interval 9 to 23. Okay, so this is our upper bound for the fourth derivative. So we found big M. We found big M. Now we're going to use it. So 3. We're going to bound our error. The remainder aka the error. So we know from the Taylor's inequality definition that we were given that our remainder is less than or equal to big M times, and then we have absolute value of x minus a is 16, raised to the n plus 1, which would be 4, divided by n plus 1 factorial, which would be 4 factorial. And we want to evaluate this for the m value that we found. Here's our m value. And we want to also evaluate it for two different x values. So evaluate when x equals 16.8 and when x equals 22. So we look at these one at a time. We know that remainder, that error, is less than or equal to 0.00066682 times, if we put in the 16.8, we'll have absolute value of 16.8 minus 16, all raised to the 4th power, all divided by 4 factorial, which is equal to about, let's see if we can crunch this thing. So it'll be 0.000668682 times 0.8 to the 4th power divided by 24. So I've got that my remainder is less than or equal to 0.00000114. So what I want to point out is this is a very small number. Very small error. Let's do the same thing when x equals 22. So if we do the same thing when x equals 22, we have that the remainder, the error, aka the error, is less than or equal to same m, 0.000666682, but now we have 22 minus 16 raised to the 4th power, all divided by 4 factorial, which would be equal to all that same stuff, but my 0.8 is now a 6. And so my error is 0.03, or my max error, 0.036. Okay. This is a larger max error. So let's make sure you see what's happening here. So we really have two things going on. So one thing that's happening that I want you to see is that when we estimate at 16.8, we're looking pretty close to 16, close to that center point. And when we're close to that center point, we have small error. Close to that center point, you've got small error. That's cool. When you go at 22, that's much farther from the center point, and so you'll have a large error. Close to the center, small error. Far from the center, larger error. So that's the first one thing I want to point out. The second thing I want to point out is that we now have an inequality. Remember, this is an inequality around the error. Okay, saying we know something about our error even without knowing the exact value of the function. And so this gives us a bound. It says the worst that our error could be in the first case is about 0.00001. It's a very small error, and we can know that even without knowing what 1 over the square root of 16.8 is. We're also able to determine that the max error, the worst case scenario for 1 over square root of 22 is no worse than being off by 0.036. And again, we're able to find that worst case maximum error without knowing the actual value of 1 over square root of 22. So that's why this error bounding remainder theorem is so valuable. It gives us a maximum worst case scenario for our error without requiring that we know the exact value, which is the very thing that we don't know. Otherwise, we wouldn't be doing this estimating in the first place. So practically speaking, on the calculator, you can think about the calculator evaluating the sine function. The calculator knows it only shows 13 decimal places. So it says, how many terms do I need to use in my series in order to have my max error be smaller than whatever it is to 13 decimal places. So it's like that gives you, that's part of why that precision is so important on a calculator, and also why they can break down if you kind of go to a greater degree of accuracy than they are able to track. Example 7. Determine the number of terms of the Maclaurin series for e to the x that should be used to estimate e to the 0.1 to within 0.00001. So this is a question about number of terms. It's sort of like the question earlier that used the alternating series test, except for here it won't be alternating. So let's remember our Maclaurin series. So it's e to the x equals, for Maclaurin series, so it's centered at 0, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot, 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 right? And if we want to find e to the 0.1, we need some sort of an error bound that goes with that e to the 0.1. So let's so we know that e to the 0.1 would be equal to 1 plus 0.1 plus 0.1 squared over 2 plus 0.1 cubed over 3 factorial plus 0.1 to the 4th over 4 factorial plus dot, 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 dot. But we want to know how far out do we need to go to be within this 0.00001 of the final result. So let's play with that error bounding formula for the Taylor series, which also works for the Maclaurin series. So we know that we need to find that big M. So we know that big M is always bigger than or equal to the n plus 1th derivative of f of x on some interval, absolute value on some region. So we got to pick a region. Well, we can't go up to 0.1 because that's the value that we're actually trying to look for. Maybe if we wanted to go to something nice, if we went to like ln of 1. So if we let our interval here be from, I don't know, minus, if I go to ln of 1 is 0, it's a little hard. So if I go to minus ln of 2 less than x less than positive ln of 2, I don't know, that's something to work on. Let's just try it. And so if we did that, notice that our nth derivative of e to the x is always e to the x. So we want our m, we're saying our m is always going to be bigger than or equal to e to the, it's an increasing function, so it's going to be biggest at ln of 2. Like it's going to be smallest at minus ln of 2. And so this whole thing would be equal to 2. So we could choose from this, since m has to be bigger than or equal to that, we could just choose big M to equal 2. Okay, so we found big M. So now we got to find our remainder. Find Rn of x. So we know Rn of x is always less than or equal to m times the magnitude of x minus a, or a is 0, raised to the n plus 1th power over n plus 1 factorial. In our case, if we substitute these things, what we know in, and this is a magnitude of the remainder. We know that the magnitude of the remainder, our error, will be less than or equal to m, which is 2. And then we know that the x that we care about, we're given that x is equal to 0.1. So that's going to be our x value. So we're going to have absolute value of 0.1 is the same as 0.1. So I have 0.1 to the n plus 1 over n plus 1 factorial. And we want this remainder to be under the 0.00001 that we were given. So let's see, let me just double check that I get enough zeros. So this is what's given. And so from that, we can force our remainder is already less than this thing. And so we could say, well, if we also force it to be less than or equal to 0.00001, let's see what happens. So we got to ask ourselves, what n will make this statement true? And we can sort of just try different values. So I'm going to, so if you think about this, this would be like n and our upper bound, our max error. So if I let n equal, say, if I let n equal 1, so then we're saying our max error is 2 times 0.1 to the 1 plus 1 or 2 over 1 plus 1 or 2 factorial, which is, well, that'd be 2 over 2, so that would be 0.01. Is that less than 0.00001? Nope, it's not true. So this is, we need to get bigger than n equals 1. So we try n equals 2. So when we try 2, we get 2 times 0.1 to the 3 over 3 factorial. So I'm going to get this going on my calculator. So I have 2 times 0.1 to the 3rd power. I know this isn't going to work, but I still want to be able to type it in and make this work a little faster. So this would be 0.0003 repeating. Again, this is too big. It's bigger than 0.00001. So fail. So then 0.0003 repeating is also bigger than 0.00001. Once again, we fail. So now let's try it at 3. So we try it at 3. We'll have 2 times 0.1 to the 4th power over 4 factorial, which will be 4 factorial, 4th power. I've got 0.0234583 repeating. Ooh, this is smaller than 0.00001. Success. So what does that tell us? So it says, our question was, determine the number of terms of the Maclaurin series that should be used to estimate e to the 0.1 to within 0.00001. And so our answer is we need oh, that's a little big, sorry. We need n equals 3 terms. That is, e to the 0.1 is approximately equal to 1 plus 0.1 over 1 plus 0.1 squared over 2, 0.1 cubed over 3 factorial, which is 6. Okay, plus or minus 0.00001. And so we could add those numbers up and kind of compare and see how it works. So if we look at these terms right here, at 1 plus 0.1 plus 0.1 squared divided by 2 plus 0.1 cubed divided by 6. I've got from that 1.1, oops, sorry, 1.10516 repeating, and that'd be plus minus 0.00001. And if I try out just on my calculator, and if I try out e to the 0.1, I get e to the 0.1 is equal to 1.105170918. If we compare 1.1051651 5, 1. And then notice 6 repeating would be the same as a 7. And so we are, what's the difference? There's no difference until we get to the 5th place. So there's no difference. We're within things. Our only difference is there. That's the plus or minus 0.00001. So all told, what have we done? We have determined, come on. We have determined the number of terms in the Maclaurin series that we would need in order to find e to the 0.1 within this type of error bound. So we've got some bonus questions. Example 4. Find the first 3 non-zero terms in the Maclaurin series for f of x equal to e to the x times sine x. And this is kind of fun. And it involves remembering a couple things. So first, we're going to remember that e to the x is equal to 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, et cetera, et cetera. And also remember that sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, et cetera, et cetera, et cetera. And then we can multiply. And so to multiply, think about taking these two things and multiplying longhand. So we're going to find e to the x sine x. And we're not going to find the whole thing. We're just looking for the first 3 non-zero terms. And so maybe I'll start with my x, and I'm going to multiply that x times 1, and that x times x, and the x times x squared over 2. So that'll give me x plus x squared plus x cubed over 2 factorial plus x to the 4th over 3 factorial plus da 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 da. Okay, so these were all of the blue guys. Okay. And then we can move over to the next term and the x cubed, and we can multiply that x cubed over 3 factorial times each of the terms in e to the x. So this would be plus, and I'm going to line it up. X cubed over 3 factorial. So this would be minus x cubed over 3 factorial, and then plus x to the 4th over 3 factorial, and then minus, oh wait, sorry, that was a minus as well. These are all minus. Minus x to the 5th over 3 factorial. Da, 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 da. And I think you're getting the picture, but let's do one more. Okay, so if we did one more, maybe we hit yellow. So we'd take the yellow term and we'd multiply it by the e to the x stuff and line things up. So x to the 5th over 5 factorial times 1, that would be plus x to the 5th over 5 factorial. Yeah, that's work is running away from me. For 5 factorial, and then plus x to the 6th over 5 factorial plus x to the 7th over 5 factorial plus da 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 da. The question asked us just to find the first 3 non-zero terms, and I think it should be clear that those first 3 so we can multiply. So now our third step is going to be to add. And so we're just going to add, and we're going to get e to the x sine x is approximately equal to x plus x squared. And then we have x cubed over 2 factorial minus x cubed over 3 factorial. So that's 1/2 minus 1/6. So that would be plus 1/3 x cubed. And then it's going to continue on, like the next term out, it looks like is going to be, also looks like we have x to the 4th over 3 factorial minus x to the 4th over 3 factorial. So maybe there's no next term, plus 0 x to the 4th. And then I have minus x to the 5th over 3 factorial plus x to the 5th over 5 factorial. So that's a 6th. The negative plus a 1/20th. Oh my gosh. Negative 1 over 6 plus 1 over 120. So this would be like then minus 19 over 120 x to the 5th plus da 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 da. It's going to continue on forever and ever. But it's like it's like multiplication elementary school style, but you're now doing it with infinitely long polynomials, which is kind of rad. So all together, we have found the first 3 non-zero terms in the Maclaurin series for f of x equal to e to the x times sine x. Example 6. Find the Taylor series for f of x equals cosine x centered at x equals pi, and I want to graph f and t3 together. So we need to start by finding the Taylor series, which means finding a whole bunch of derivatives. So we have f of x is cosine x. F prime is minus sine. F double prime will be minus cosine. F triple prime will be positive sine. Fourth derivative will be the cosine. The fifth derivative will equal the minus sine, etc., etc. And so here's our functions. And then we can evaluate at x equals pi. And so we know that cosine of pi would be -1. Sine of pi is 0. +1, 0. -1, 0. So it's bouncing back and forth, starting with -1. So this means that we're saying that cosine of x, we're saying cosine of x is equal to -1 from here. And then we have plus 0x from here. And then we have plus 1 over, I guess this would be 2 factorial times x minus pi squared. Oh, that should have been, I'm sorry, this should have been an x minus pi over here. But it won't change anything because it's times 0. And then, so that's this 1 is coming from here. And then we're going to have plus 0 over 3 factorial times x minus pi cubed. And that 0 is coming from here. And then minus 1 over 4 factorial times x minus pi to the 4th. And et cetera, et cetera. And so I think we can see what's happening here. This is going to go plus dot, dot, dot. So I think you should be able to see, you can see that cosine of x will equal minus 1 plus 1 over 2 factorial x minus pi squared plus 1 minus 1 over 4 factorial x minus pi to the 4th plus 1 over 6 factorial x minus pi to the 6th minus 1 over 8 factorial x minus pi to the 8th, et cetera, et cetera. All right. And so if we want to find T3 in this case, it's a little bit, there's a little bit of ambiguity here of what we're saying when we talk about T3. So we know what our f is. So f of x is cosine of x. But T3 is the third degree Taylor polynomial. And in this particular case, humorously enough, there's only even powers. So in this particular case, our T3 of x will just be the minus 1 plus 1 over 2 x minus pi quantity squared. Right? Because there is no cube term. So we just have the constant and the squared term. So let's actually change it because I think it'll be a little bit more interesting. So let's make this a T4. So we'll add one more term in here. So we're looking for T4 now. Let's just update our notes. T4, come on. Our fourth degree polynomial. And so we'll add, or I should say subtract, 1 over 4 factorial, which is 24, x minus pi to the 4th power. And so the question asked us to graph these things together. To graph them together. So let's see if we can pull up our Texan friend and graph. All right, so we're going to try to graph the function f of x equals cosine x, and then also the T4 function. So let me share my screen. And here I've taken the liberty of entering the two functions into my y equals. So here's our, in y1, here's our f of x. And in y2, here is our T4 4th degree Taylor polynomial we're using to approximate the cosine. So let's see how these look together. So I'm going to set my window, and maybe I'll choose the classic trig window. So I'll choose zoom 7. So there's my cosine function, and you can see here's our fourth degree Taylor polynomial. And you'll notice they look pretty doggone good right here in the middle. What's right in the center of this nice section? Oh, they look good in the region around pi. Where's my eraser? So they look good around pi, but the farther you get from pi, the worse the approximation looks. So maybe it's a little bit cheesy, but let's just draw this into our notes so we remember what's going on. Here's our x and our y. And so we have our cosine function, which looks like this forever and a day, and it's going to continue oscillating. And here's pi, and our approximation, our T4, looked something like that. And it looks like it goes right through the origin. There. So this is our T4 of x, and here was our cosine of x, just by way of reference. Let's check if we've answered the full question. So the question asked us to find the Taylor series for f of x and cosine x, or f of x equals cosine x and T4, and graph them together, and we have done that. Yay! So once again, you see the Taylor series gives you a nice approximation for this function, and the center matters. Center point matters because that's where the approximation is most valuable. So last little question part here is why would it be beneficial to center a series at x equals pi? And the answer is pretty simple. So you would want to center at x equals pi if you are interested in values of cosine x near x equals pi. For example, imagine that you wanted to find like the cosine of 3 or the cosine of 2.9 or the cosine of 3.14, right? All these values, 3, 2.9, 3.14, they're all near x equals pi. And so this approximation would be pretty valuable for you, much more valuable for you than a fourth degree approximation that was centered at 0, for example. Example 3. Approximate the integral from 0 to 1 of e to the negative x squared dx to within 0.001. Whew. Okay. This is an important question. It's actually ties to statistics. And what's important to note is that there is no closed form antiderivative for this. We actually need to use power series to evaluate this integral. So we're going to start by dealing with this as a power series question, Maclaurin series question, and then we're going to take on the error bounds part of the question down the road. So it's best to begin at the beginning. So let's start with what we know. So we recall that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. So this tells us that e to the negative x squared will equal the sum from n equals 0 to infinity of negative x squared to the nth power over n factorial, which could also be written as the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over n factorial. So we have an expression for e to the negative x squared. Now we need to integrate. So that was kind of first. So second, we're going to integrate e to the negative x squared dx. And I'm going to start by ignoring my limits of integration. We'll come back to that. So this will be the integral of the sum from n equals 0 to infinity of -1 to the n, x to the 2n over n factorial dx. And the integral of a sum is the sum of the integrals. So this will be the sum n equals 0 to infinity of the integrals of -1 to the n, x to the 2n over n factorial dx, which this is an indefinite integral, so I'm going to pick up a plus c. So I have plus c, and then the integral -1 to the n, x to the 2n plus 1 over 2n plus 1 times n factorial. So I've found my antiderivative, yay. So third, I can evaluate the definite integral, 0 to 1 of e to the negative x squared dx will equal the garbage from above, c plus sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 times n factorial. And I want to evaluate this from 0 to 1. Whew. Well, we know that this plus c is going to go away. That part's easy. Let's see what happens when we put in 0 for our x. So when we put in 0 for our x, all of those terms are going to be 0. So that'll be easy. So all we really worry about is what happens when we put in 1. And 1 to the 2n plus 1 would just be 1. So this whole thing is going to just simply equal the sum from n equals 0 to infinity of -1 to the n times 1 divided by 2n plus 1 times n factorial. So that's what our integral is equal to. And so we need to simply, this is the exact value. This is the exact. And now we need to approximate this to within 0.001. Let me scroll back up to remind ourselves of the directions and verify. So we're trying to approximate to within 0.001. Okay. There's actually a number of ways that you can do this. So we want to prox within 0.001. One of the ways is that you will learn in the next class is using the, I think we might need to do that. I was going to say I was going to use the remainder theorem, but we don't really have. Do we have a Taylor series here? A number. Let's. This question's a little bit different than the last one, and so we actually have to use a technique that we haven't used before. So let me write out what's going on here, and I think it'll make it a little bit clear what I'm going to do, although the reason for what I'm going to do you won't learn until the next class. So let's think about what these terms look like. So the first term, when n equals 0, this will be, so let's see, so we have the integral from 0 to 1 e to the negative x squared dx. And so this would be 1 over 1. So I think it's just 1 for the very first term. And then we'll get minus 1 over, so n is 1 for the next term. So when n equals 1, we'll have 2 times 1 plus 1, or 3 times 1 factorial, or 1/3, plus 1 over 5 times 2 factorial, 5 times 2, and then minus 1 over 7 times 3 factorial, plus 1 over 9 times 4 factorial, minus 1 over 11 times 5 factorial, plus et cetera, et cetera, et cetera. This is an example of an alternating sum, plus, minus, plus, minus, plus, minus, plus, right? They're alternating. And with the alternating sums, where the terms are decreasing in size, we know that we know from stuff that we didn't cover in this class that the term, like the error, is always smaller than the magnitude of the next term out. So I could think about it this way. So if I just stopped at the first term and I said this integral is equal to 1, and if it's equal to 1 plus or minus 1/3, because from this next term out. Or think about here, this is 1, this would be like 1 minus 1/3 plus 1/10. 1 minus 1/3 plus 1/10 minus 1/3 plus 1/10 would be, that's 23 over 30. So you could say it's 23 over 30 plus or minus the next term out. That would be, looks like 1 over 42. Okay, so I'm always like saying my error matches the next term out. So this is the, what's this called? Something alternating series estimation theorem, something like that. Alternating series estimation theorem, I think. Which is in section 11.5, which we sort of didn't cover, but just sort of no extra charge for this, I guess. So when in the question they say we want to approximate within 0.01, we could really say, you could look back and you could say, if it's 1 plus or minus 1/3, is, I'm asking, comparing the 1/3 error tolerance here to the 0.001. Nope, 1/3 is too big. If I look at the 1 over 42, 23 over 30 plus or minus 1 over 42, I'd say, oh, 1 divided by 42 is 0.02. Too much. So I'm sort of like testing these terms to figure out which one is close enough. So maybe I could try the 11 over 1 divided by 11 times 5 factorial. So this right here, this one is, that's 0.0008, right? Which would, yeah, which looks like it would round to 0.0001 or 0.001. Okay, but it's less than 0.0001. So here it's less than that thing. So what we're saying is that the sum, if we put all this stuff together, we're saying that the sum of these first terms right here, which ones? I'm saying if we add up all of these terms all the way up that are in green, so we have, let's see what that is. That would be 1 minus a third plus a tenth minus 1 over 42 plus 1 over 9 times 24. So all that stuff is equal to 0.7475, and then it will be plus or minus the next term out. The next term out, which I think we already just found, was 0.0008. So the question asked us to approximate that integral within 0.001. Our approximation is 0.7475. And the only strange part about it is we had to use a different error bounding technique other than the Taylor series. We used this alternating series estimation theorem, which is actually quite a bit easier than Taylor's method. Yeah, so there you have this particular example. So I know this has been a really long and intense section, and some of these last examples have been pretty long and arduous. But I hope that gives you an idea of how power series work, how amazingly powerful the Swiss Army knife duct tape of mathematics is, and then also some of the nuance that goes into actually applying them to evaluate and to be useful in certain situations. I hope that was helpful, and look forward to catching you in the next lesson. Take care.